It's time for some accidental astronomy. This week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. Astronomical and planetary science discoveries often unfold in strange and serendipitous ways. This week, we dive into the delightfully unpredictable nature of our field with Chris Lintott, the author of the upcoming book Accidental Astronomy. Then Bruce Betts, our chief scientist, gives us a new way to think about the scale of our solar system in What's Up. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. Before we jump into our interview, I want to send a congratulations to my colleague Casey Dreyer, our chief of space policy. This Friday's upcoming space policy edition of Planetary Radio marks 9 years of his monthly reporting on the state of space advocacy and policy. Casey's show on the complex human interactions that shape the progress of space exploration are always super insightful, and I cannot believe it's been 9 years. Our monthly space policy edition of Planetary Radio comes out on the first Friday of every month, so you should definitely check it out. And now for some accidental astronomy. From chance observations to fortunate circumstances, breakthroughs in astronomy and planetary science frequently emerge from the intersection of curiosity and coincidence. But that's part of the fun. It's a field where any observation could become a game changer as we explore our star system and the vast universe beyond. Our guest today, Dr. Chris Lintott, is a professor of astrophysics at the University of Oxford. He's best known as the co-presenter of the BBC's Sky at Night program, but he's also the author of The Crowd and the Cosmos and the co-author of Bang. His newest book, called Accidental Astronomy: How Random Discoveries Shape the Science of Space, explores how happenstance shapes the history of space discoveries. One decision or a lucky cosmic event can turn into decades of exploration. Accidental Astronomy comes out next week on Tuesday, June 11th, 2024. Hi, Chris.
Hey, how are you?
Doing well. Thanks for joining me from the UK.
Yeah, it's a pleasure to be here. I'm a big fan of Planetary Radio, so it's nice to be on the show.
Oh, that's lovely to hear. And I had a really fun time reading your book, because anytime I come out of a book with this feeling of just awe and wonder, that's a lot of fun. But in this case, it was specifically this idea that most of the discoveries that we end up making in astronomy really happen by accident, which is an interesting thing to grapple with.
Yeah, I think it really does change your feeling about the cosmos as well, once you realize that really we've been stumbling over truth in astronomy and planetary science for the last century or so. I think it's very easy to feel like, the universe is challenging us to be clever, that when you look up at the night sky and think about all those thousands or millions of planets, those worlds waiting to be discovered, the mysteries of cosmology, the vastness of the solar system, I think it's quite easy to feel quite small in that environment. And yet, I think if you realize that there's nothing required of you other than attention. And yet we've been able to make discoveries of wonders in the solar system, of the grand theories that we know about the cosmos, of all sorts of unusual and wondrous things. Then I think it takes the pressure off a bit, and we can relax and enjoy being sentient beings trying to understand the cosmos. So that was a large part of the feeling that I was aiming for in writing the book, in telling these stories of accidental discovery.
I think, too, that it's really valuable for people to understand, especially if they're going to be going into our field, that you do not have to be this absolute genius to make these discoveries. It's not these people that just go, Eureka, I've discovered something. It is a happy accident and the people working together to try to piece together these mysteries of things you've discovered.
Yeah, one of my colleagues talks about fighting the Hollywood version of science, which is where we all sit in a surprisingly well-appointed conference room in big chairs, waiting for somebody to leap up and say, my God, I've got it! And at that point, we all just run and launch a spacecraft or make an observation and decide that we're all clever before tea time. And of course, it's not like that at all. Science is about being unsure. It's about being surprised by things. It's about being the person in the room saying, are we sure that that's right? And that's where discovery comes from. And so a large part of what I was thinking about when I was compiling the book and writing these stories was getting away from this idea that only the smartest can play this game. Anyone can be an astronomer, can be a planetary scientist, can think about the cosmos. And with luck and perseverance, we can all make discoveries.
But a lot of these discoveries take much preparation. We need our instruments to be all perfectly tuned for these kinds of discoveries to happen. So in these moments where we are trying to discover something, but then we accidentally stumble upon it, like how do you define accidental astronomy in that context?
It's obviously the case that if you go and sit under a night sky and wait for something to happen, you're unlikely to get very far. Though, maybe there was a time when that was sufficient. I think a lot of the time, these are discoveries that depend on a certain kind of perseverance of a group of scientists willing to pull data out of the noise, to look where others are looking. We can talk about an example, I think, which is the wonderful discovery of the fountains of Enceladus, of water coming from the South Pole, of what was thought originally to be a small, fairly boring, icy moon. And what's interesting about that story is that when the Voyager probes visited the Saturnian system, there were people who noticed that Enceladus was unusual. It's very shiny, basically. It's one of the most reflective surfaces in the solar system. And there were a couple of papers in the 80s that said maybe this was interesting and put forward some hypothesis involving a fresh surface, but no one really thought much of it. And then when Cassini arrived in the Saturnian system, it wasn't supposed to pay much attention to Enceladus at all. And yet when it happened to fly by, the magnetometer team, who was supposed to be studying Saturn's magnetic field and how it interacts with the surroundings, basically decided to record data as they went past Enceladus as a test. They were looking to take their instrument, newly arrived at Saturn after a long cruise, out for a test drive. And it was from their data that the first hints that led us to this discovery of an ocean under the moon's icy surface were made. But the interesting thing to me about it is that, apart from all the wonders of Enceladus, of course, which we could talk about, is that there's one thing to decide to test your instrument by leaving it on as you go past Enceladus and sort of have a look at the data. But I think it would have been very easy for Michelle Doherty and her team to just check that it was working, that data was being recorded, that stuff was being saved to the hard disk, and then get on with the mission that they prepared for. But because they're a particular kind of curious and interesting bunch of scientists, they dug deeper. They did the data reduction. They noticed that there was a change in magnetic field as the spacecraft went past Enceladus. And then Michelle flew to JPL for a meeting to persuade the other scientists on the Cassini project, some of whom, it has to be said, didn't need much persuading, that they should go closer to Enceladus, that they should turn the cameras on when they did. And that was when people realized that we were looking at water spraying into the space out by Saturn. So that moment of perseverance is really important in a lot of these stories. So obviously, Michelle and her team were well trained. They built the instrument, they got it funded, they got it to Saturn. None of that happens by accident. But because they did that and because they were curious, they made this discovery that no one was expecting.
I can't even imagine how history would be different, how our upcoming missions would be different if that hadn't happened.
I mean, yeah, and just on that, if that hadn't happened, or if the other people on the Cassini team hadn't been willing to change their plan. They have the magnetometer team. I don't think Michelle would mind me saying they're often slight outcasts, right? Magnetic fields are odd things. Their data looks very different. Their scientific objectives are very different. Imagine if she'd gone to JPL and everyone had said, no, look, we've got a mission that we planned. We spent a long time working out what we're doing. Let's do that, and then we'll worry about Enceladus later. That could easily have happened.
And in this context, this is what's so fun about this book, is they've stumbled upon this discovery, and then it leads us down this rabbit hole of other discoveries, because there was this moment in the past where the Galileo probe to Jupiter discovered a very similar thing with the magnetometer when it went by Europa. And now we think perhaps that's because of the underwater or the subsurface ocean on Europa, very similar to Enceladus. So all of these things end up connecting together. And now we're looking down a moment in time where we're sending an actual mission to Europa, the Europa Clipper mission, to go investigate this. And I bet none of that would have happened without this moment with the people at Enceladus.
That's right. And, I should mention as well, sitting over here in the UK, we also, of course, had JUICE, which is the European mission to Europa and Ganymede, which is on its way already. So we're very excited about that. But yeah, it's sort of this idea. It's interesting how quickly this idea becomes a normal part of planetary science. When before the Cassini mission, we were sort of in a situation in which, people had speculated about oceans at Europa and Ganymede in particular, but I think the consensus was that they were deep features, that they were a long way down under the ice rather than nearer the surface, as we hope they are now, and that Europa Clipper and JUICE will hopefully confirm. But now we just think about oceans everywhere. People have proposed an ocean under the ice for some of the features that we see on Pluto, for example. So talking about Pluto as our dynamic world. When we think about extrasolar planets, when we think about planets around other stars, and we start thinking about habitats for life, yes, we'd still like to find some Earth-like planets, for whatever definition of Earth-like we're using. But when we see a giant Jupiter around a star, well, maybe it's got moons that have life in this sort of Enceladian mode. And so it's become normal to think of new possibilities of life, all coming from this, what started as a strange blip in a reading of Saturn's magnetic field.
I love this discussion, too, about the creatures that might be living inside of these moons. We haven't actually discovered life off of Earth yet, but you bring up in the book that if there were to be intelligent creatures trapped under the ice of these worlds, they might not have eyesight, and they might not even be aware of the broader universe beyond that ice shell. So it brings up all these really interesting kind of sci-fi ideas of what life might be like under the ice. And also makes me feel very glad that we live on this terrestrial world where we're even capable of looking out into the universe and being able to receive light from beyond, because that really changes our perspective on where we are in the cosmos.
Yes, it was very tempting to start writing the sci-fi trilogy of the intelligent ichthyosaurs or dolphins from Enceladus exploring the broader cosmos in an icy bubble as they break out for the first time. But I mostly restrained myself. I think potential readers will be pleased to know. But it is interesting to think about the biases of our place on Earth. You can imagine a learned symposium in the Enceladian Ocean, and I don't think it's likely that there's intelligent life there, but there might be. You can imagine them discussing how they can ignore any possibility of life this close to the sun. After all, we're on the surface of a world. We're exposed to cosmic rays, to solar activity. This would be a ridiculous place for life to exist. Much better, when we think about life in the cosmos, to consider only life that's protected by a proper icy layer separating a safe, pleasant ocean from the cosmos beyond. So yeah, you do see that our perspective can shift quite quickly, which is quite fun. But it's also fun to think about what physics such intelligent beings would have. Would they know that they were in orbit around Jupiter? And I think if you think it through, you probably come up with experiments that could be done that would tell you that you were in a world that was in orbit. And having known that, who knows? Maybe we'll see some intelligent Enceladians come to visit us one day. But for now, we're going to wait and try and go to them. I know the European Space Agency has said its next outer solar system mission will be a trip to Enceladus. So I'm very excited to get back and find out what's in that water.
And then we can compare the two, because the readings that we've gotten out of the plumes when Cassini did that flyby through the plumes suggests that there's hydrothermal vents inside of that moon, which is an indication that it could be very good for life. I can't even imagine what we could see if we went back there, or perhaps what would happen when we get to Europa and try to see if there are actually plumes there, because I know there is some indication from Hubble data that there might be some plumage out of that moon as well.
Yeah, people have seen water from Hubble. And again, those observations were awarded. The team got time on Hubble only after we'd seen the fountains of Enceladus. So, although there were previous hints that there was an ocean on Europa, no one had thought to look for it venting into space. There are hints of water in a couple of observations, I think. But the question is whether they're coming from the main ocean or whether there's a separate source of water, maybe relatively shallow, underneath the ice that's breaking out there. So these are things that we need probes in situ to measure. And I think one of the things that I learned from writing the Cassini chapter, which I was thinking about the other day, was the difference between the marvelous flyby missions of the past. I was lucky enough to be at Mission Control when New Horizons went past Pluto, and that was a marvelous moment, and we got our data, and the images are iconic, of course, but it's very different when you have a probe like Cassini or JUICE or Europa Clipper, when they're able to go into orbit and explore systems, to spend time somewhere properly, to get to know the local moons and their features. So I'm really looking forward to some of these long-lived missions that can do more than just fly by these places and can really help us explore them.
Imagine a future where every single world has its own orbiter. What we could discover. It would be amazing.
It'd be nice, wouldn't it? Just a permanent. I mean, that's not a ridiculous thing to want. I think it's it seems strange to me that we don't have anything in orbit around Saturn right now for the low cost of these things.
Or out to Uranus and Neptune. There's so much about those worlds that we don't understand.
That's true, and of course they're good analogues for what we see elsewhere. And it's another accident. I'm not sure it's something that I mentioned in the book, but when we started looking for planets around other stars, the assumption was we were looking for solar systems like our own, and yet we found this huge diversity of worlds, with Jupiter's very close to their star, with lava worlds, with all sorts of patterns of planets, large and small, that we didn't know it could exist. We've also found, I think slightly to people's surprise, that things a little bit bigger than Neptune and Uranus are the most common type of planet. So again, that's not something you'd realise from looking at our solar system. Sorry, it's things a little bit smaller than Uranus and Neptune are the most common type of planet, somewhere between them and the Earth. And that's a type of world that we don't even have in our solar system. So there's another surprise there.
I'm really glad that we have things like JWST to help us understand those worlds better, because it's a weird thing to think that maybe our solar system is an outlier. But again, that's just our human perspective.
Indeed. And there's a chapter in the book about looking for life on Venus, of all things, of the results that came out in 2020 of the discovery of the chemical phosphine high in the atmosphere of Venus, work led by my friend Jane Greaves down the road in Cardiff. And phosphine's exciting because on Earth, it's only made by life, mostly in the stomachs of penguins, it has to be said. And so seeing it on Venus was, Jane was carrying out those observations as sort of proof of principle that you could, at those wavelengths, look for this chemical, thinking about one day doing this in distant systems around other stars. And then they got this signal and to be honest, weren't quite sure what to do with it. If you go looking for a biosignature for a chemical that only exists via life on Earth, and then you find it, you find yourself in this quite strange position of having done a test for alien life and found some. Now, I don't think I know Jane wouldn't claim that they've produced definitive evidence for life. We don't understand the chemistry of Venus's atmosphere well enough to be able to make that claim. Maybe there's some exotic process, something volcanic or something in the strange acidic atmosphere of Venus that produces this chemical. But that was a huge surprise to everyone, including the researchers. And I think it's a good example of another type of accident where it was worth making those observations, not quite on a whim, but without necessarily believing you were going to find something. Sometimes it's worth going on these fishing expeditions, and no one had looked at those wavelengths of Venus before. Venus is very bright in the millimeter waves that they were using, so they had to adapt the telescope software to be able to look at Venus at all. It's also quite close to the sun. You normally don't point telescopes like this, which have super cooled instruments, anywhere near the sun, so they had to work out how to do that. But that effort meant that they made this discovery, which has inspired all sorts of speculation about potential very simple alien life, which has inspired new models of the Venusian atmosphere, and which maybe has stimulated a couple of private missions that might go back and take a close look at the chemistry of the atmosphere. Plus, it was great fun hearing from Jane. I was lucky enough, I worked on a BBC programme that some of your listeners might know, The Sky at Night, and we got an exclusive to go and interview Jane about this. And in the build-up to that, it was in the middle of the strangeness of the pandemic, so we went and found her in a deserted physics department, and we were trying to work out how to frame the story. We wanted to convey the excitement, but not say, astronomers at Cardiff have definitely found aliens. And my first question to Jane was, well, what do you think you found? She said, well, it could be alien life, but, and I thought, brilliant, we've got the interview. She said that, and then we could chat about all the detail and about the complexity of it. But I was so giddy that I'd got that first line that in all of that reporting, I'm just grinning manically because it's so much fun to have this secret, this unexpected discovery land in our laps.
It was really fun for me because at the time I wasn't working on Planetary Radio, but I was listening to it every week. And when that episode with Jane Greaves came out about this discovery of potentially phosphine on Venus, we got flooded with people sending us art of penguins on Venus, just penguins flapping in the clouds, penguins partying on the surface.
Yeah, no, it's definitely penguin. There's something about penguins, I think. I know Emily Drabak-Maunder, who is now a science communicator but was a postdoc, got recruited to the project because Jane walked into her office and said, "Do you want to look for penguins on Venus?" So even the researchers are playing that game as well. Oh, yeah, we should say, by the way, that some of your listeners may have followed that there's a bit of saga in that many other astronomers didn't believe the detection. So not just didn't think that the detection implied alien life, but there were lots of questions around whether there was really phosphine seen in the data at all, or fitting this sort of spectrum's a bit of a black art. But I had confidence at the time. I've known Jane for years, and she's a black belt at this kind of thing. And I was able just to get into the book an update from new observations that I think are pretty conclusive that there really is phosphine there. So the penguins in Venus are there to tease us yet.
This is one of those discoveries that you really do need to verify, because the search for life is one of the greatest questions humanity has ever been posed. And I love that you point out in the chapter about, is it aliens, this idea that astronomers are really bad at keeping secrets. If we did find something that was an indication of that, even if they tried to keep it a secret, just people slewing the telescopes that direction if they found a signal, or people using extra instrument time to look for specific things, would be a dead giveaway that people had discovered something cool.
Yeah, the way I've been putting it, because we've been getting involved in SETI here in Oxford, so we have the Breakthrough Listen project are now based here. So I've been beginning to work on this sort of stuff. My academic interest aligns with the book in that my main academic interest is finding unusual things in large surveys. So this all hangs together. But yeah, I've been telling people that the trouble is that the world turns faster than your brain does. So in other words, even if you take traditional SETI, where what we think we might detect is, I know, some prime numbers flashing from a particular radio source on the sky or something like that, before you're sure that that's real, before you've ruled out all the systematics, you've checked that it's not your laptop malfunctioning, that there's not a drone flying, the thing's going to set. So before you're sure, you have to tell the rest of the astronomical world. And so I think it's functionally impossible for radio astronomers, at least, to keep the discovery of a potential SETI signal quiet. We'll have to tell each other. And then, yeah, whenever something unusual does happen, the astronomical world knows about it pretty quickly. I remember when there was the first discovery of a flash of light accompanying a detection of gravitational waves, of ripples in space, back in 2017. We've only seen this combination of something in the electromagnetic spectrum and gravitational waves once. But this was all supposed to be very secret until the paper was published. But because pretty much every telescope in the world was pointing at the same part of the sky, and pretty much, I think we worked out in the end, something like a third of astronomers were involved in following up on this discovery. Pretty much everyone knew what was going on and was excited. So this is a game this game of being surprised is a collaborative one, and it's a game we play together, and that just adds to the joy of it.
I mean, that moment with LIGO is in and of itself a great example of why so many discoveries happen necessarily by accident. Because we've been trying to find these colliding black holes and compact objects for a long time and had made some detections with LIGO. But it wasn't until these two neutron stars collided that we could have a visual thing on the sky that we could really point our telescopes at and validate that this LIGO project was actually working in the way that we thought it was going to.
That's right. And there's also a wonderful result that came from, I think it's a 3-page paper that was written maybe even the day after the thing happened, which is that you can measure the speed of gravity because the gravitational waves arrived to within the galaxy that we have at the same time as the light, even though they traveled for hundreds of millions of years to reach us. So we now know that, as predicted by relativity, gravity travels at the speed of light. But how wonderful to have an experimental test of that because of an unspeakably violent event that happened in a distant galaxy that we're able to detect in these ways. I think, actually, in talking about the book, I think there's this claim early on. So I'd nearly finished writing the book, and I was struggling a bit to explain to people what it was. Hopefully I'm not doing that now, but to set up the book, to explain why I wanted to talk about accidents and accidental discoveries. And I had a drink with the wonderful Meg Urey, who is a professor of astronomy at Yale. She was one of the people who worked out how black holes and galaxies live together. And Meg is very wise and very smart. And so we were sharing a gin and tonic, and I was telling her about the book, and she said, look, I don't think there's a single discovery single big discovery in 20th century astronomy that wasn't made by accident. And I thought, brilliant, that's going in the introduction, and it's there. And I think I can stand by that, except that it's possible that LIGO, the detection of gravitational waves, may be a mistake. That may not have been an accident, because that was the result of 30 or 40 years of people building increasingly sensitive detectors, aiming for a goal without knowing where the end post was. They just knew that they had to keep improving the sensitivity, and at some point they'd find these gravitational waves, and they'd succeeded in great measure just a few years ago. So I think they possibly get points for being the only people in astrophysics who behave like Hollywood scientists. You know, they've got a goal, they work towards it, and yet the universe has surprised them, because we've discovered that black holes exist at different masses than we expected, that neutron star collisions are more violent than we expected, and so we are still being surprised. But I think that maybe they get half a point for knowing what they were doing.
I mean, it took a lot of planning since the beginning of us even understanding what gravity was. I believe Einstein would never have believed that we would have been able to figure out how to detect gravitational waves. That's so wacky.
No, well, even black holes, you know, right up until the 50s and 60s, they were viewed as sort of, even beyond that, actually, they were viewed as sort of theoretical curiosities, the way we would talk about a wormhole today, right? Yes, you can make the equations behave that way, but no one really thinks that these infinitely dense objects that can prevent light from escaping would actually exist, let alone play the role in the cosmos that we know that they do. So it's only really with the development of high energy telescopes and then large telescopes that let us look at the distant universe that we realize that black holes play a central role in the life of each galaxy. They were supposed to be some crazy theorists thing that you played with as a curiosity as an undergrad and then moved on to more serious stuff.
We're also very lucky that we could have that rating of the two neutron stars colliding, because it fundamentally changed the way we thought about how elements are created in the universe. We thought a certain number of these things were created in supernovae, but it turns out a large number of the high-end metals are actually made in these neutron star collisions. I would have never guessed that.
No, there were people who'd predicted some of this, but what was great about these observations was they let us quantify that for the first time. So we can see how much gold was made in just that one collision. And conveniently, if you're wearing jewelry, or your listeners are, then gold in particular seems to have been mostly made in these collisions, not in stars. So we're beginning to realize that the stuff we have around us has this diverse history that comes from supernovae, from explosive events, but also these more exotic things like neutron star collisions. And that means that stuff that they produce has to get mixed in the galaxy. For the gold to have ended up here on Earth, it must have been mixed through the disk that the planets were formed on. And that means that you don't just have a supernova polluting its neighbors, you have that material being mixed around the galaxy. And I think we're only now beginning to learn with data from things like the European Space Agency's Gaia satellite, how dynamic a place the Milky Way and other galaxies are, how you don't just sit where you are. You know, results from Gaia tell us, for example, that the stars like the sun, so if you take a star on the sun's current orbit, there's a 50-50 chance that it will have spent some of its life much closer to the galactic center than we are now. And that's kind of interesting. I think I've certainly thought that the galaxy was stable, that the sun would continue in its orbit forever, just as the Earth's going to continue in its orbit until the end of the sun's life. But things are much more complex and dynamic for that. And to bring us back to a previous bit of the conversation, that has consequences for life and habitability, I think, out here on our vulnerable rocky planet. Then if you swing close to the galactic center where there are more supernovae, where there are maybe more of these neutron star collisions, you're suddenly exposed to a very different environment than where we are now. So there may be lessons for our history or for life in the universe from these things as well.
I think you actually bring that up in the section on asteroid Bennu and the OSIRIS-REx mission, when you're talking about trying to predict how long it might be before that asteroid comes by and potentially impacts our planet. No matter how good our understanding of physics is, anytime you have more than 3 bodies interacting, it's really hard to predict what's happening that far out. So trying to understand what's happening in an even more complex system like the entire galaxy is a really difficult thing to do, and necessarily means there's all kinds of adventures that we can't even foresee.
That's right. It's a bit like trying to write about the history of an institution or a country or even the human species, you can come up with broad rules for why things are the way they are and why they turned out this way. But there are also, things like the battle that didn't happen because it rained on a Wednesday, or the invention that came 100 years earlier than it would have done in one particular place, all these contingent events that change everything. And we have that, of course, in astronomy. We've been lucky that the sun seems to have produced quite a stable planetary system. There are some hints that there was a recent study, actually too recent to go in the book, but that showed that 1 in 4 sun-like stars seem to show evidence of having eaten planets over the course of their lives. So it may be that we're in a surprisingly stable place, that we haven't had this nearby supernova, that we have stayed at roughly this distance from the center of the galaxy, that we haven't had an asteroid impact. The counter that says days since asteroid impact, a significant asteroid impact, is up to 65 million years. And I'm fascinated by this idea with Bennu that I think in the old picture of science, the Hollywood picture of science, you'd think that with enough computing power, with enough observations, we could predict where Bennu's going to be for as long as you want into the future. It's just gravity. It's not that we don't understand the physics. But because, as you say, things get complicated when you have to take into account the pull of the other planets, and because there are effects like the effect of the sun or the sun's radiation on the asteroid and various other things, we can't really do a very good job more than 100 or 200 years in advance. And in particular, there's this keyhole moment in about 80 years' time, where Bennu will come quite close to the Earth, and it definitely won't hit, but exactly how close it comes will determine what happens 100 years hence. And there's nothing we can do except wait for that moment and then look and see where Bennu's ended up. Of course, we can plan. We can go and visit it. The OSIRIS-REx mission did this. I was hugely privileged. I managed just a couple of months ago, I was visiting my friends at the Natural History Museum in London, just down the road, and they let me hold their bit of Bennu in a test tube, I hasten to add, but this thing that the spacecraft had gone and collected, and then they took it off me so they could go back to analysing it and trying to understand the composition of this thing. But just for a moment to hold, having watched OSIRIS-REx, I was going to say touch down, but sort of encounter the rubble pile that turned out to be Bennu and see these spectacular pictures, and then to be sitting there holding a piece of this asteroid that the spacecraft had brought back, that was quite a moment.
We'll be right back with the rest of my interview with Chris Lintott after this short break.
Hi, y'all. LeVar Burton here. Through my roles on Star Trek and Reading Rainbow, I have seen generations of curious minds inspired by the strange new worlds explored in books and on television. I know how important it is to encourage that curiosity in a young explorer's life. That's why I'm excited to share with you a new program from my friends at the Planetary Society. It's called the Planetary Academy, and anyone can join. Designed for ages 5 through 9 by Bill Nye and the curriculum experts at the Planetary Society, the Planetary Academy is a special membership subscription for kids and families who love space. Members get quarterly mailed packages that take them on learning adventures through the many worlds of our solar system and beyond. Each package includes images and factoids, hands-on activities, experiments and games, and special surprises. A lifelong passion for space, science, and discovery starts when we're young. Give the gift of the cosmos to the explorer in your life.
I was really lucky. I got to speak with Dante Loretta recently about the OSIRIS-REx mission because he came out with a book about it. And what was amazing for me was that mission in large part only happened because of the coincidence of the Shoemaker Levy 9 impact on Jupiter, which you also talk about in your book. I had no idea how important that one moment with multiple objects impacting Jupiter was to this moment in history with our mission to go to Bennu. And imagine if that hadn't happened, and if Bennu potentially could have hit Earth in the future, we might not have known any of that without that coincidence of something impacting Jupiter. It's wild to just kind of see these moments of fate just kind of woven together.
Yeah, and that's a good example of how sometimes a single event that's not hugely significant in itself. Jupiter's fine, right? The fact that a comet hit it in the early 90s hasn't had any long-lasting effect, although I guess Schumacher 11.9's not as well as it used to be, having disappeared into Jupiter's atmosphere. But watching that happen, I think, just changed how people thought about the solar system. They suddenly saw that it was a dynamic place. And that was a discovery that was made by accident. The Schumachers and David Levy were comet hunting, but they weren't looking for comets that were going to hit Jupiter. And they saw this unusual thing. And whenever you find something unusual, it demands explanation. So they saw this string of cometlets and realized that it was Jupiter's gravity that had ripped the comet apart and that they were going to impact. And, from a personal point of view, I think this might be the moment that set me off on the astronomical course that I followed of looking for unusual things and thinking about serendipity, because I was a school kid at the time with a small back garden telescope, and all the coverage had pointed out correctly that the impacts happened basically on the far side of Jupiter as seen from Earth, so we didn't get to watch the impacts directly. The Galileo spacecraft got a distant view because it was at a different angle, but nothing on Earth could see the impact. And so you had to wait a couple of hours for the impact site to rotate round onto the part of Jupiter that we could see. And all of the coverage said, try with a small telescope, but basically don't expect to see anything. The Jupiter is big, the comet is small, the amount of energy isn't large. And I remember looking through my back garden telescope on a summer's evening, a couple of hours after the first impact, and just seeing this bruise on the surface, seeing Jupiter like I'd never seen it before, and that no one remembered seeing it before. There were it turns out, from a couple of hundred years ago, there were a couple of recorded instances of people saying there's a very dark spot that's appeared, but no one, certainly for hundreds of years, has seen this, and no one until that evening had seen that happen to Jupiter and know what it was. And we got this week of comet bit after comet bit after comet bit hitting the planet, and these bruises building up around the surface, and then we watched them fade over the next few weeks. And I got to watch that through a small telescope. Admittedly, I did that first night, I woke my parents up and got them to drive me to my school where there was a much bigger, we were lucky there was a bigger observatory, but I remember trying to explain to them that we needed to go now because something was happening on Jupiter. I'm very grateful that I'm not sure they listened, but they certainly got me to the bigger telescope. But so that was a moment where I think a single observation, a single event changed how I think about the cosmos, but how lots of us do. And it's interesting to hear Dante point to that as well. I've tried to tell him a bit about the Osiris-Rex mission, but we hadn't had that conversation.
I just love the idea of you trying to drag your parents out of bed to go see this. That's something I would have done as a kid. Yeah. That would just seem to, maybe it's an astronomer's instinct, right? You've seen something, get me to a bigger telescope right now. Right now. This also brings up for me the section in the book about the interstellar asteroid Oumuamua and the accidental discovery of this object, which we, at least as far as our observations can tell, is the first interstellar asteroid that we've discovered so far. And I love that idea that we might have these objects, and to go back to this idea of everything in our galaxy kind of mingling together. Our solar system in and of itself isn't purely self-contained. You have these objects flowing through interstellar space, maybe just cruising through a solar system every once in a while. And who knows what might happen if one of those objects impacted a planet like Earth early in our formation.
Yeah, or not just the planet. So these things so we've seen two of them. So Oumuamua gets all the press because it was first and because it was slightly weird. And then, and then
Borisov.
And then Borisov, which turned up and looked like a comet, which is what everyone expected. And I think is neglected, sadly. It's sort of like the Apollo 12 of interstellar objects. It was important. It taught us a lot, but everyone remembers the first one. So we think that there are something like 10 to the 27. So what's that? That's a billion of these things in the galaxy. So that makes them the most common thing in the galaxy. Thing that's bigger than an atom of hydrogen anyway. And no one had given them much thought until one of them happened to come through the solar system and be spotted. The thing that got me really interested in Oumuamua and its many friends is, as you said, this idea that they might visit the early solar system, that we think today that density that I told you, the number of them, implies that there's an interstellar object passing through our solar system right now. There's almost always one this side of Neptune. We're currently pretty bad at spotting them. We've only seen two. But that flux would have been roughly the same for the history of the Milky Way, would have increased a bit over time, but not by much. And so that means that when the solar system was forming, our disk from which the planets were assembling is threaded with these interstellar visitors. And that's interesting because there's a problem in how we form planets. We understand how to form things that are a few tens or a few hundreds of meters across. The physics of that works quite well. That's basically dust grains, and icy dust grains in particular, sticking together and forming bigger and bigger things. And once you form something that's, say, a kilometer across, then gravity takes over, and so that accretes more material. Or if you collide two things that size together, gravity keeps the resultant rubble in one place, and you get something that's twice as big, and you can go on and build a planet. But that gap in between, if you collide things that are a few hundred meters across together, you get a pile of rubble that drifts apart. You don't get a bigger thing. And so we don't know how to do that quickly. And there are all sorts of ideas, but I think, and this is an idea due to Michelle Bannister and Susan Felsner, not mine, but I really like this idea that there's a cheat code that we can seed planets in our solar system from these interstellar objects passing through. So if they get captured by the disk, they become the seeds which go on to form the planet. So you must have formed somewhere in the galaxy at some point, there must have been a first planetary disk that managed to form large things and then scattered lots of them to the winds, and then they would have triggered this runaway process of planet formation through the galaxy. And so when we look at these interstellar objects now, we're seeing a process that might have been responsible for the diversity of planets that we see.
Wouldn't that be interesting if we could look out with a large telescope in space, try to find that moment in history and see if it really does kind of cascade out from a central planetary system or something? It'd be really hard to get that much data, but wow, what a discovery.
The first step, I think, is that we can find more of these things. So I'm involved with the Vera Rubin Observatory, which is an 8-meter telescope that's going to do a survey of the sky. We're really excited. Our 3,200 megapixel camera just arrived on site in Chile, so things are beginning to feel pretty real. And we think that one of the things Rubin's going to be great at is giving us a catalogue of solar system objects, because if you're surveying the whole sky with an 8-meter telescope, you spot stuff that's moving. And we don't really know, but we think we'll get somewhere between 10 and maybe a few hundred interstellar objects. So we'll go from having 2 to having several hundred, and then we can start to say things about the places that they come from. We can start to say things about the types of protoplanetary disk that scatter these things to the stars. So we're right on the threshold of going from we've only got 2 of these things to, I guess it's Monday, we found another interstellar object. I guess we'll put that in the pile. And that change over the next 10 years is going to be really exciting.
It's really interesting to see just how fast our understanding of the universe has accelerated because of these discoveries. And I'm thinking specifically about the Hubble Deep Field that you mentioned in the book. And that discovery in and of itself just being a moment when they pointed the Hubble Space Telescope, which you also say is it's really hard to get time on a space telescope like that. And then they went and pointed it at absolutely nothing at all and ended up with one of the most pivotal images in the history of astronomy.
That's right, and it pioneered a way of doing astronomy that we still do today. I mean, we've all seen the JWST results in the last couple of years where, we just broke the record for the most distant galaxy. JWST spends a lot of its time staring into blank space, but it was surprising to me that Hubble was never meant to do the deep field. It wasn't in the original missions plans. It's not why Hubble was built. And there are papers by very eminent astronomers, people who know what they're talking about, published just before the deep field was released, that argue that Hubble will discover no new galaxies. That you can use this telescope to study things we know about, but it's not going to discover anything in deep space. And the error that they'd made was a simple one. They'd assumed that the early universe was like the universe we see around us today. And it's true that if you take the Milky Way and you put it far enough away that its light has taken, say, 10 or 11 or 12 billion years to reach us, Hubble's not powerful enough to see it. But it turns out the early universe is full of fireworks. The galaxies are forming stars at a rate that we haven't seen since. The black holes at the center of these galaxies are actively consuming material, and material glows brightly as it falls down. So we have this much more lively universe to look at, and we didn't know it was there till they looked. And so then the question is, why did they look? And the story here is great. Hubble, as many of your listeners will know, had a checkered past. It was launched with a malformed mirror. It took a lot of ingenuity and a space shuttle mission to go and essentially fit corrective optics to fit glasses to its cameras so that it could see clearly. And all of that took a great toll on the team who were building and running it. And they were pretty tired by the time 1995 rolled around. So that's 5 years after launch, something like that, and 3 years after this repair mission. And they'd been running at full pelt. So the director of the Space Telescope Science Institute wanted to give his team something easy to do over the holidays. And so the deep field at least had the virtue of being a simple observation. You just keep pointing the telescope at the same thing for 100 hours. And so it was scheduled over the holidays in 95 so that they could run a skeleton crew and just get this simple observation. And then the plan was just to release the image, whatever it showed, at a meeting of the American Astronomical Society in Seattle in January 1996. So as the photons were fresh off the camera, and it was an astounding moment, this unveiling of this image, and the sudden realization as you look at it that everything you're seeing is a galaxy. It's not a field full of stars. It's a glimpse of a universe that's filled with galaxies. And, I think it's going right back to where we started the conversation. I think, if I'm talking about this on stage or on camera or to anyone, to a taxi driver or somebody in the pub, very easy at this point to go, and yes, to imagine that each of those specks of light is just a galaxy of 100 billion stars, each of them the equal of our sun, and get this sort of cosmic awe thing going. But I also like the fact that we can look at this amazing image, know what it is, and realize it was essentially made in the face of scientific orthodoxy because people wanted an easy time over the holidays. I think it's important to have both of those thoughts in your head when you look at the deep field.
It brings me back to the beginning of the book, too. Just all of the coincidences that had to happen along the way in the universe for us to even be here at all to make these discoveries. It's absolutely beautiful and really startling when you think about it, and kind of makes this human journey even more beautiful and strange, I think.
I think that's right. Beautiful and strange is a good description of the cosmos. And I think it is both beautiful and strange that we happen to live at a time where we have a spectacular cosmos to observe. That won't be true in a few tens of billions of years once all the stars have finished forming. So we're lucky there, but also that we live at this time in human history that because of all the contingencies that we talked about, because of the way that technology has advanced, that we not only get to understand the cosmos in this golden age of astronomy, but we also get to ride along with missions like Europa Clipper. We can be fans of those things and follow as the data hits down on Earth. It still astounds me that if you're up at the right time and you hit refresh at the right time, that anyone can be the first person to see an image sent back from the surface of Mars. If I could have told the 14-year-old kid who was observing Shoemaker-Levy 9 that was going to be a possibility, I think his eyes would have fallen out of his head just having that sort of access. So we are very lucky.
We really are. I do feel like we're living in a golden age of astronomy, which is just so fun for everyone like us that loves this kind of stuff. And there are so many stories in this book I wish we could get to, but I don't want to spoiler it for everyone. But I do want to say I had so much fun diving into this book and just kind of, marveling at the fact that we are just really lucky to know what we do about the universe. And I really wonder what we're going to stumble upon in the next 100 years that might just blow the lid off of everything we know.
Yep, well, no doubt the book is out in, just next week. So no doubt the greatest discovery ever made will be the end of next week. And I'll have to start rewriting immediately.
Well, thanks so much for joining us, Chris, and for this book. And I'm going to leave information on our website at planetary.org/radio about how people can find this book and read it themselves.
Great. Good stuff. It's been lovely talking to you, and it's a privilege to be on the podcast. It's really fun.
Thanks so much for joining me. It's honestly a bit mind-boggling. Just think about all of the random and beautiful moments that have allowed us to advance this far in our understanding of the cosmos. And the fact that we're even here at all is amazing. Here's to all of the stars that lived and died for their elements to be spread out across time and space so that we could be here to look up and wonder together. Now, let's check in with one of my favorite humans, Dr. Bruce Betts, our chief scientist for What's Up. Hey, Bruce.
Hi, Sarah. Top of the glorious space day to you.
I understand that you've met our guest for this week, Chris Lintott, before, but it was a while ago, right? It
was a disturbingly long while ago, since it seems like it wasn't that long ago, but I think it was way back in the aughts, just past the turn of the century. Yes, I don't know if Chris remembers our wild night on Palomar, but we went up to Palomar, and The Sky at Night, the British long-running show, he was doing a segment for them, and they invited me to go up and try to see the L-Cross impact into the moon with the Palomar 200-inch, and we didn't see anything, so I think the footage is probably kind of funny, but I've never seen it of both of us staring at a TV screen and then wondering, it should have hit by now, right?
It sounds like he's got a long history of trying to go see impacts on things. He told me the story about his time trying to go see Shoemaker Leaving 9 as a kid, and how formative that was for him.
Yeah, no, it's neat. And other people did get observations, but looking at with Palomar, we didn't. But had a good time.
I still haven't been to Palomar. I should do that.
Oh, it's pretty amazing. I spent during my grad school years, I spent 12 glorious nights under clouds and rain and not getting any observations that I was going to get. But I learned how to play cowboy billiards because they have a billiards table in the giant dome underneath. So.
Sounds awesome. I wonder what the weirdest things that are actually inside observatories are. Like, I know at Lick Observatory, underneath one of the big telescopes, Lick is actually buried. There's a tomb underneath it.
I was going to make a joke about a dead body, but there actually is.
There actually is, yeah.
Wow. Yeah, no, that's great. I look forward to hearing the interview with Chris. It has been many, 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 many years since we communicated.
Well, it's a cool premise for a book. Because honestly, you can prepare all you want. You can create the instruments. You can have the scientists that trained all their lives to learn certain things. And in the end, so much of astronomy is just this kind of stumble upon into the mysteries of the universe, just because everything is so big necessarily. Like even just finding planets, you have to wait for one to transit across a star. It's weird when you think of astronomy in that context.
Part of the nature of our business, astronomy or planetary exploration, is exploration, and that you don't know what you'll find. You plan all you can by your guesses, but sometimes you just happen to be looking the right way at the right time or some other permutation.
Before we move on to the random space fact, I wanted to share something that I thought was really cool that I read in our member community. A lot of our listeners will probably remember a few months ago, I had some people on from a National Geographic documentary called The Space Race that was all about the first African-American astronauts and space explorers. And in that documentary and in that interview, we talked to Ed Dwight, who was supposed to be the first Black astronaut, but was denied the chance to do that because of political reasons and everything that fell out during the Apollo era. But just recently in May, I learned through our member community from Laura Monahan and Bob Ware, two of our members, that Ed Dwight actually did get to go to space just recently with Blue Origin. So he finally got to go to space and became the oldest person to go to space.
I missed that. That's awesome.
Right? That's so cool. I have to have him back on.
Yeah. No, it's great.
All right. What's our random space fact?
Random space fact.
That sounded like that hurt.
Oh, it did. It did, actually. All right, I got a scale model for you.
Okay.
Solar system, let's grasp the majesty of the solar system. If the sun is hanging out, as it does, in New York City, and Neptune, as it does, is hanging out in Los Angeles, then Earth would orbit at about the distance of Philadelphia. So sun, New York City, Earth, Philadelphia, Neptune, all the way across the country to Los Angeles.
Man, the solar system is so big, and then you realize how small it is in the context of everything, and it's just...
No, don't go there.
Don't think about it, Sarah.
Don't think about it, Sarah. We'll lose you for a few minutes again. Stay here. Stay local. Not the local group. No, local here in the solar system. It's big enough for all of us.
These scale models are always trip me out. It's like you see it on a page, you think you understand, and then it's not until you're like walking one of those scale models or, thinking about it in that context that you really realize just how much empty space is out there. I'm really glad we get to live on this beautiful rock.
All right, man. All right. Hunky-dory swell. Go out there, look up the night sky, and think about what type of glasses you would wear to watch gerbils hunting ants on a sunny day in Bermuda. Thank you and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with the return of Radiolab's Latif Nasser. Get your submissions ready because it's time to name a quasi-moon of Earth. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review and a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email at planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members who love the thrill of discovery, accidental or not. You can join us as we help shape the future of space exploration at planetary.org/join. Mark Hilverda and Ray Paoletta are our associate producers. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. And until next week, Ad Astra.